Hi, in this session, I will show you how to generate a PWM waveform in VHDL. And in the next session, we will implement it on FPGA board. So we will generate a PWM signal of 1 Hz with 50% duty cycle. And we will see the results on the real LED. I will tell you that how you can adjust your duty cycle of your PWM signal. And of course, frequency as well. I will show you that what are the important parameters that you need to consider for getting a very specific PWM signal. Means very specific duty cycle and frequency of your PWM signal. So let's start. So question is that how do we generate a PWM signal in an FPGA? And the easiest way to generate a PWM signal is using a counter. So it's kind of a register which is increasing its value at every clock cycle. And once it reaches to a certain value, which we will define, then it is set to 0 and then keeps incrementing once again at each clock cycle. So look at this graph here. Here x-axis is your counter value with respect to time, which is your y-axis. And you can see that your counter value keeps increasing with time until it reaches to this maximum value. And then at this maximum point, it comes back to 0. And on the very next cycle, it starts increasing again. And this is happening continuously. Now, question is that what will be this maximum value for your counter? So this is basically a deciding factor of your PWM signal. And it will decide your PWM period or frequency, you can say, or PWM cycle, you can say. So this is one parameter to decide your PWM period, and it is very important. There are more parameters also to decide this periodicity. For example, your input clock frequency or your FPGA board frequency. Like in our FPGA board, we have a 50 megahertz clock, which we will use. So for this 50 megahertz clock, we will have a 20 nanosecond of clock period. Means one cycle will complete in 20 nanosecond. It is just a simple math. You divide 1 second over 50 megahertz and you will get a 20 nanosecond. This means that our counter will increase by 1 at every 20 nanoseconds because we are increasing our counter at each clock cycle. And for 50 megahertz clock, each cycle takes 20 nanoseconds. Now, if we want a 1 second period for our PWM signal, which we are generating, then the question is that how many counts we need if we are increasing our counter at every 20 nanosecond. So it is simple math again. We calculate 20 nanosecond for one clock cycle of 50 megahertz and we want 1 second PWM signal. So divide 1 second by 20 nanosecond. So your answer will be 50 million times. Means our counter need 50 million increments to get exact 1 second. Note that our clock frequency is 50 megahertz and we are calculating it for this clock signal only. If your clock frequency is different, then this number will be different too. Just use a simple formula to get the total number of increments, right? So for this 50 million increments, we start our counter from 0 and we will count it up to 49 999 and this will be our 1 second. And once we reach at this number, that is 49 999, then our counter will reset to 0 again for calculating next 1 second. So it is in the loop. This odd number is because we are starting counting from 0, not 1. And this number is actually 1 less from 50 million. Okay, so don't get confused. Now look at this waveform again. So we start our counter from 0. Then we are increasing it continuously at each clock cycle. And we reach to this maximum number. That is 49 999. And it is our exact 1 second time. Now we reset our counter to 0. So you see that after 49 999, our counter starts counting again from 0 to get another 1 second. And at this point, it will again complete counting of 49 999. means we get another 1 second. So this counter run continuously in this cycle, like from 0 to 49, 999. So each time it completes counting from 0 to 49, 999, we get exact 1 second. And because this process is repeating over and over again, so we have this periodic waveform. So you see, we marked each second on the time domain here. So this was cycle duration, means we get 1 second repetitive cycle. And PWM pulse will have rising edge and falling edge between this 1 second cycle. So the question is that how we can set the duty cycle of our PWM signal. If you do not know that what is PWM duty cycle, then in simple word, it is the ratio between how long your signal remains at logic 1 and how long your signal remains at logic 0 state on one single cycle. So how we will achieve this? Simply, we need to pick a value from this counter range. That is from 0 to 49, 999 in our example. And that will decide your duty cycle. For example, suppose we want to generate a PWM signal with 50% duty cycle. This means that for 50% of the time, our signal will be at high state. And for rest 50% of the time, it will be at low state. So let's say we pick this point marked with this blue line, and it is halfway between 0 and 50 million, means 25 millions around. So this value will be used to set PWM duty cycle. So let's see how it works. We will monitor our counter value and we will compare it with this blue line point or this intersection point value. And if our counter, which is red color inclined line, because our counter is increasing at every clock cycle, reaches to this point and intersect with this blue point, we will change our output. For example, if the value of our counter is below this line, then we will set our PWM output to 0. And when our counter is above this line, then our PWM output will set to 1. So let's see this in the graph. So look at this region first. Our counter starts from 0 and it reaches up to this blue line, which is 25 million. So up to this point, our PWM output is 0. Now for this reason, when our counter, this red inclined line, counts from 25 million to this upper threshold, which is 50 million, then our PWM output is 1. Now once we reach at this upper threshold, which is 50 million here, we has interesting thing. So you can see that at this point, our red line come back to 0. Because at this maximum point, we reset our counter to 0, right? So at this point, our counter value is below this blue line. So our PWM output goes 0. Now the counter starts counting and slowly it will reach to this blue point. So till this point, our PWM output remains 0. And once we reach at this blue point, our PWM output will be 1. Again, it reaches to this maximum point. And until then, our PWM output is 1. And at this point, our counter reset to 0 again. So our PWM output become 0. And you can see that this is happening again and again. So we will get this continuous PWM output. So the question is that how it will control your PWM duty cycle. So let me tell you that this PWM output is actually has 50% duty cycle. Why? Because it is low for 50% of the time and it is high for rest 50% of the time during one cycle. Like you see 0, 1, 0, 1, 0, 1. Now to change the duty cycle, what you need to do? You just need to pick another point for this blue line. For example, if you increase this blue line pointer to some higher value, then you will see the reduced duty cycle. Because till this blue point, your PWM output is low. And above this blue point, your PWM output is high. And you see now our output signal is at 0 for longer duration and it is at 1 for shorter duration. For example, here we have reached this intersection point. So now our counter will take longer time to reach to this point. And for that period, our output is 0. And above this point, the output is 1. So you can see that our output is 1 for shorter time compared to the logic 0. So we get reduced duty cycle, something like 20% in this case. So if you want exact 20% duty cycle, then get 80% of 50 million. And that will be your intersection point. Simple. Now, on the other hand, if you lower down this blue line pointer, for example, something like here, so you may guess that our counter will be below this line for shorter duration and above this line for longer duration. So our PWM output will be high for longer duration and at 0 for shorter duration. Means you will get higher duty cycle of your PWM signal. So this is the hardware block representation of our design, or you can say flow chart as well. So we are needing this counter, and in our case, it is driven by 50 megahertz clock cycle. And this is our blue line intersection point, or you can say duty value. And we will compare this value with our counter value. So in our project, we are developing 50% duty cycle signal. So this value will be 25 million in our case because our counter is counting from 0 to 50 million roughly. So 50% is our midway, that is 25 million. Don't worry because we will be developing this system in the real FPGA in the next session. So we will compare this counter value with this duty value, which is 25 million. And if the counter value is less than this duty value, then our PWM output will be 0. And if the counter value is greater than this duty value, then our PWM output will be 1. So that's how we can control the PWM cycle and PWM duty cycle. Means if you need higher duty cycle, reduce your duty value. And if you need shorter duty cycle, then increase this duty value. And if you want to change your PWM cycle, then you can control it by changing your maximum counter threshold based on your clock frequency. So that's whole story short. I hope this is clear to you because in the next session, we are developing it into VHDL and then we will implement it on FPGA board as well. So stay tuned for the update. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video and don't forget to share. Thank you for watching.